name's Sheila. I'm the Education, Outreach and Diversity Officer at the Royal Astronomical Society. And today you are joining me on a journey to Saturn to meet the Lord of the Rings, no pun intended, and the Cassini-Huygens mission, which was a flagship mission to Saturn and its rings and its moons in the 1990s and 2000s, which I worked on as part of my PhD. So I've had a really cool career. I'm really lucky to be where I am today. I was introduced or inspired into the space industry when I was 13, and I saw the film Apollo 13, and that just made me, that sort of blew me away about space and made me think, yes, I would like to be an astronaut. So I read about astronauts in my local library, and one of the routes into the space industry to be an astronaut is the academic route. And I read about a couple of astronauts, Helen Sharman and Michael Foale. And Michael Foale had a PhD in astrophysics. So when I was 13, I decided I was going to get a PhD. Didn't really understand what it meant then, but that is what I decided I was going to do. So I studied science and physics at school. I went to Manchester University and did physics with astrophysics. And then my PhD was in planetary science at the Mullard Space Science Laboratory. And on the way, during that journey, I also taught astronomy at Space School UK, and I travelled all over the globe doing different types of astronomy and space science. But it was the PhD that really inspired me into learning more about Saturn and the Cassini spacecraft. And it's some of the data, not from my PhD, but from the Cassini mission that I'm going to present to you today. Just quickly though, I work for the Royal Astronomical Society, which is a learned society representing astronomers and geophysicists across the globe. We are an international organisation, but most of our members are based in the UK. And our building is in central London. Obviously it's shut at the moment, but if you are ever in central London and want to have a look at our lovely library or come and meet us, please do feel free. That would be great. Our first president was William Herschel back over just about 200 years ago. Now, William Herschel, his picture's on the bottom left there. He was the astronomer that first identified Uranus, and he did a bunch of other amazing astronomy too. And he had a fantastic sister, Caroline Herschel, who was the first woman to win our gold medal in 1828. And she discovered 8 comets, and she was the first woman to be paid to be an astronomer as well. And one of our more recent presidents, on the right-hand side of the picture on the bottom left, is Professor John Zarnecki, a planetary scientist just like me. But the reason I show these two pictures side by side is because you can see that the perceived field of astronomy and the kind of idea as to what astronomers look like hasn't really changed much in 200 years. But hopefully you can see that I'm an astronomer and a planetary scientist, and I don't look like that. And hopefully in the next 200 years, we can inspire a new wave of astronomers and geophysicists to learn more and more about our solar system and our galaxy and our universe and beyond. So the Cassini mission and Saturn, for me, really started when I was doing my PhD. But of course, the history of Saturn goes back much further. And it starts with just move that. And it starts with Galileo, who was the first to really observe the rings, but he observed them over time and he observed them incorrectly with a puzzled gaze because the ring orientation changed over time. And he thought that what he was seeing was a centralized planet and 2 smaller planets or moons, and that the larger planet ate the other one up when viewed at equinox. At a similar time, but in a different place, there was Huygens, who built a telescope, and he made the telescope and the lens. But his colleague Dirk, the chimney sweep, made the telescope tube. And Huygens used this telescope to really look at the rings around Saturn, although he thought the rings were one solid ring instead of lots of separate ones. And he discovered the great moon Titan in 1655. So a few years later, There was Cassini, who discovered some of the Cronian satellites, where Cronian means Saturn. Saturn satellites like Iapetus, Rhea, Tethys, and Dione. And he saw this division in the rings that we call the Cassini division. And Huygens wasn't happy that there was competition looking at Saturn, but it was really good. It was healthy competition because it drove Huygens and Cassini to do more and more discovery about Saturn. And it's quite ironic now because the Cassini-Huygens spacecraft will go down in history with those two names together as an incredible partnership, whereas in real life, Cassini and Huygens were competitors in the world of astronomy. So planetary science is a bit like those voyages in the past to discover different continents. You would have to take everything you need with you. The missions could take tens of years. You don't know what you're going to find when you get there. You don't know whether you're even going to survive. And it's a bit like driving your car from London all the way up to Scotland, leaving it running, leaving it by itself, and going back to it in 20 years' time and expecting it still to be working. Now, planetary science is a relatively, well, planetary exploration with technology is a relatively young science. Planetary exploration started in the 1960s with the Russian space program, when they sent Venera 1 to Venus. This looks a little bit like a Dalek, but it was a space probe to Venus. It wasn't successful, but a few years later, there was Venera 7 that landed on Venus, and it was the first time human beings had built something that landed on a planet outside of the Earth. It recorded about half an hour of data and then a bit more a few weeks later, but it was really, really successful, and it drove planetary science for future years to come. So the Cassini mission is was quite a long time coming. The idea and the concept behind the Cassini mission started in the 1980s, and then there were various studies done and proposals put in before NASA, the European Space Agency, and the Italian Space Agency confirmed that Cassini was going to be built and launched. It was launched in 1997. It took 7 years to get to Saturn, and then the mission was supposed to last 4 years. But actually it was so popular and it worked so well that it was extended and extended until 2017, when the end of the mission included the Cassini spacecraft burning up in Saturn's atmosphere. So for some people, that was a 35-year mission. It was as long as, sort of the age of a person. So if you were involved in the Cassini mission from the beginning till the end, it was really quite moving for you, and you got really, really into working with Cassini and working with the data that was coming from Saturn. It was a really international mission as well. There were 19 countries contributing to building hardware. There was 12 different instruments and scientists from all over the world taking part in this amazing mission. It was really a flagship for NASA. It was a huge spacecraft, and you can see there's the Cassini spacecraft with some people at the bottom for scale. And it had all kinds of different bits of hardware. It had something like 14 kilometers of cabling, 22,000 connections. It was a very smart spacecraft. It could run alone for 10 weeks. It took about 9 hours to send data back to Earth from Saturn, with about a 1.5 hour delay. It had a 1 megapixel camera on it, which took photos in black and white. But used color filters to give us some natural color and false color images. And on the side of the main spacecraft bus, was the Huygens probe, which was a mostly European and British-led mission, which would then detach from the Cassini spacecraft, and the probe would land on Saturn's biggest moon, Titan. And at the beginning, the Cassini team was relatively small. This isn't all the team. This is just the assembly, test and launch team. But the team was quite small. And by the end of the mission, there were hundreds of people that had worked on the Cassini mission. And I feel really honoured and privileged that I was part of that, even though I was just a small part of that as part of my PhD. So on Cassini, there were 12 different instruments. They ranged from measuring the magnetic field to looking at the dust, to taking pictures, to looking at the particles, so the electrons and the ions in the Saturn environment. There was also the antennas, which would send the information back to Earth, and the engines and the thrusters to change the orientation of the spacecraft. And the different instruments had different teams. So there were 12 different teams which would get the data from that instrument and analyze that data. And so you were working separately in your team, but you also had to work together as a collective. And you had to there was a bit of compromise because, for example, if the magnetometer team wanted to measure the magnetic field this way, which meant that Cassini had to move in a particular direction, then that might be challenging for the team looking at the dust. And so you had to kind of work together to make sure that the spacecraft was always pointing in the right direction at the right place in the right time. Now, I worked on the electron spectrometer, so that was built at the Mullard Space Science Laboratory, which is part of UCL in London. And the electron spectrometer was bolted onto the main body of the spacecraft and measured electrons in the Saturn environment. And I particularly looked at the magnetic field of Saturn and how that interacted with the planet, the rings and the moons. And it was a really interesting project. It was very, very computational. I'd get spreadsheets full of data and I had to use computer programming to analyze that data. But it was, although it was challenging, it was eye-opening because whenever I got kind of bored or bogged down in those numbers, I could think these numbers have come all the way from Saturn, and that became really exciting. So over the years, Cassini racked up a lot of numbers. It was really quite impressive in terms of the distances it had travelled and the data that had come from it. After 10 years at Saturn, Cassini had travelled 2 billion miles. It had taken over 300,000 images. There had been 132 close flybys of Saturn's moons and lots of nations participating in analysing data. And this is a picture of some of the Cassini team towards the end of the mission, and you can see it's expanded hugely. It really was an international team, and it had a really amazing family atmosphere because people had worked on the mission for so long. They really cared about the data and the spacecraft and almost personified the spacecraft into a child or a pet. So when the mission ended, it was quite emotional, and I'll show you some photos towards the end. So Cassini launched in 1997. It took 7 years to get to Saturn, and that's because it used something called the gravity assist or slingshot. So it orbited around other planets to use their gravity as fuel before going past Jupiter and then to Saturn by 2004. And during the beginning of the mission, everything was in hibernation, but it was woken up towards the end of the journey and did take some images of Jupiter and some data from Jupiter up to Saturn as well. Whilst it was orbiting around Saturn, it also looked at many of the moons in detail and used the gravity of Titan, of Saturn's largest moon, as fuel. And this was quite clever because obviously the mission couldn't take enough fuel to last for that long, and it couldn't even use solar power because it was so far away from the sun. So it used nuclear power and also gravity assist to power it through those years. And during that time, it didn't just orbit the planet, but it also orbited Titan, Enceladus, and some of the icy satellites, some of the smaller icy satellites as well. And you can see how many orbits there were around Titan, partly for this kind of petrol and partly for scientific analysis of Titan. So from July the 1st, 2004, Cassini was in orbit in the Saturn system, and over those almost 14 years of its lifetime, the data that has been coming back from Cassini has been used basically to rewrite the textbooks about Saturn and what we know about planetary science. So over the years, we also were able to teach an old dog new tricks, so to speak. So Cassini was built in the 1990s, but while it was in orbit around Saturn, new things came up, and different focuses to the mission were also introduced. So the Cassini team from Earth were able to reprogram aspects of Cassini to make it look at different areas of the Saturn system that it might not have known to look at when it was programmed at the Earth. So it really, really was a very, very clever spacecraft. Now, in terms of what we know about the planet, we know that Saturn is about 10 Earth widths across, but it's a gas planet. It's mostly made from hydrogen and helium, so it's less dense than water, which means that if you could find a giant bath and put Saturn in, it would float. Saturn's famous for its rings, and in these pictures here, you can see, move me again, you can see the rings here, they're blue. On the bottom left picture, you can see the rings are blue because of Rayleigh scattering. And on the top right and bottom right pictures, you can see the rings with a moon in the background. And then on the bottom right picture, what you're looking at is the very thin black line is the rings edge on. So the rings are very, very wide. They're millions of kilometers wide, but they're only tens to hundreds of kilometers thick. So they're very wide, but very, very thin. And because Cassini was in the Saturn system for almost 14 years, it was able to look at Saturn at various different orientations. So Saturn is tilted to its axis, just like the Earth's tilted, which means that the orientation of the rings changes depending on where in its orbit around the sun it is. And being at Saturn for so long was really useful because we saw this change in orientation, but we also saw a seasonal shift as well. The Cassini spacecraft learned a lot about the moons of Saturn as well, and of course it took lots of amazing pictures, and I'll show loads of these pictures during the course of this talk. I could look at these pictures all day long. So they're really, really clever and really, really cool. This is one of my favorites. I have a version of it behind me in my office. This picture is called The Day the Earth Smiled, and it's from 2013. And what you're looking at is kind of like an eclipse of Saturn. So the sun is in the background, and Saturn, the planet, is in shadow, but the sun is illuminating the rings and sending shadows across the surface of Saturn, or reflection, sorry, across the surface of Saturn. And I really like this picture because you can see the rings in all their glory. You can see the inner rings, which are made up of solid particles, dust and rock. And you can see the E-ring, the outer bluish ring, which is made out of water vapor and ice. And until 2005, so during the Cassini mission, we didn't exactly know why the E-ring was so different to the other rings. And I will tell you why later on. The other thing that's interesting about this picture is that you can see the moons in the picture as well, if you've got really good eyesight. And at the bottom right, you can also see the Earth and the moon as viewed from Saturn. And it's called the Day the Earth Smiled because on that day, there was a social media campaign saying, at this time, on this day, please look up at the sky and smile and wave. And Cassini was positioned so it was taking a selfie of the Earth, or a picture of the Earth from Saturn. So that's what the Earth looks like from Saturn. Now, Saturn's a gas planet just like Jupiter, and it's got storms on it, just like Jupiter's Great Red Spot. The storms can last for months. They don't last as long as Jupiter's Great Red Spot, but they can last for months. This one lasted 9 months. And it wrapped around Saturn so long that it actually kind of caught up with itself and started eating its tail. And these storms are very hot, so you can see it in different temperatures here. And some of the mechanisms for these storms and the heating processes are still unknown or undiscovered today. So there is still a lot of data from the Cassini mission to go through and to work out why Saturn is the way it is. This is one of the most intense storms, and it also gives off a lot, or it also gave off a lot of a chemical called ethylene. And we don't know where that came from, because on Earth, ethylene is created by natural and man-made sources. And obviously there aren't similar processes on the surface of Saturn. At the North Pole of Saturn, there is a hexagonal vortex or stream, a bit like a hurricane or a tornado, but it's specifically hexagonal. It's almost perfectly hexagonal. And it, here you go, you can see it at the top of the North Pole. And what was interesting about this hexagonal hurricane was that it changed colour over time, and that was because the seasons changed over time, and we went from northern hemisphere winter to summer, and this seasonal change caused the gases in the hexagon to change colour as well. And here you can see couple of gifs of these hexagons and of this hexagon. And the interesting thing about the hexagon is that the reason it's so particularly shaped and it stays like that, it stays in that shape, is because Saturn is a gas planet. So if you imagine wind on Earth flowing over the rocks and the rivers and the trees of the Earth, the wind would duck and dive and change shape. Whereas on Saturn, there is nothing underneath the wind to make it change shape, which means it can stay in this beautiful exact hexagon, and why it's so long-lived. So it's a really interesting feature at the North Pole of Saturn, and it's really beautiful too. So I will keep showing beautiful pictures every now and again. The other thing that Saturn has is aurora, or northern lights, just like the Earth does. It's got a magnetic field and it's got an atmosphere, and it does interact with the sun and the high stream of particles coming from the sun called the solar wind. So it does have northern lights or aurora as well. Now, in terms of the rings, because Cassini was there for so long, we were able to see the rings at different orientations, which meant we learned a lot more about the rings than we would have done if we'd only stayed at Saturn for a few years. The rings are not solid rings. They are made from mostly solid particles, and gas and water vapor as well, but lots and lots and lots of particles. So you couldn't sit on the rings. You can fly through them, and they're made up of lots and lots of mostly solid particles. And they are really glorious. And like I said before, they are very, very wide, up to millions of kilometers, but they're very, very thin, only tens of kilometers in terms of height. And again, the photos are quite incredible. Now, within the rings, there are lots of different features, and there are some moons that live within the rings as well, and cause features to appear on the surface of the rings as well. And these little moons are called shepherd moons, and they actually shepherd the material from the rings into place, and they keep the rings in the right orientation. And while we were at Saturn, the Cassini mission was able to investigate some mysterious features on the rings. So in this little animation, you might be able to see these dark patches on the rings. Now, those are called spokes, just like bicycle spokes. So the rings go round, but the spokes come out at 90 degrees, and they're dark patches on the rings. And we believe they're caused by static electricity almost burning the ring material. So the dust in the rings gets statically charged and causes it to become charged and create these darker features. So Cassini was brilliant in solving some mysteries of Saturn, but it also created a few questions as well. Now, this is an interesting picture of the rings from the top down, and what you can see is this ring material, and you can see the shadows of the ring material because of where the sun is. And what this is like you were looking at the pyramids in Egypt. Now, if you looked at the pyramids in Egypt from the top down at midday, there would not be a shadow. But if you looked at the pyramids from the top down a little bit later in the afternoon, because of the orientation of the sun and the pyramids, there would be a shadow. And from this shadow, you can tell lots of information about the pyramids and the height of the pyramids. And this same technique was used to work out more information about the height of the rings. And from these sorts of images, we could measure the height of the rings, and that's why we can quite confidently say the rings are very, very wide, but not very tall. And within the rings, these moons sometimes might be created, sometimes might be destroyed, and can cause some funny features and ripples in the surfaces, in the surface of the rings as well. So, for example, these propeller motions are probably caused by very, very tiny moons within the rings, causing the ring material to be kicked up. And some of the ring material can come together to actually form little moons. So, for example, this little moon was spotted in 2013, and it was named after the Cassini scientist Carl Murray. He named it after his mother-in-law, Peggy. And a few years later, he looked again at this area of the rings, and unfortunately, Peggy the moon did not survive. And there's a question here, why is there a gap in the rings? It's all to do with the positions of the moons and the positions of the rings and the material that makes up the rings, and a balance between all of that and gravity. So like I said, the shepherd moons shepherd the ring material into place, and that's particularly the solid material. And then there's the gap, and then there's the E-ring, which is made of different material, and I'll come on to why that's so different in a little bit. So the moons are my favourite area of the Saturn system, even though Saturn is the Lord of the Rings. Before the Cassini mission, we thought that Saturn had about 20 moons, but actually it's more like 50 to 60. And again, the photographs of the moons are quite impressive. This photo is again a sort of an eclipse, so you've got the sun in the background, and then the large shadow is Titan, and the small shadow on the bottom right is Enceladus, and then obviously Saturn's rings on the front again. And this shows Titan and Rhea, and this shows Saturn with 5 of the larger moons. And there's another photo here with 5 of the larger moons. Now, you couldn't ever take a full family portrait of Saturn because its furthest moon lives at 12 million kilometers from its parent planet. And the moons are named after all sorts of different things, from gods and goddesses and science fiction, Inuit names. Some have numbers, and like I said, more and more are being discovered from the Cassini data. Now, I often think about Saturn a bit like a grandparent or a matriarch of a family. So I've shown you this family portrait of my family from a few years ago now, but I want you to concentrate on the lady sitting in the chair. That's my grandma. She's just like Saturn, and she's had children and they've had children, and we're all related to that lady, but we're all completely different. And that's exactly what the moons of Saturn are like. So keep this in mind when I show you the moons. They're all related to Saturn, but you'll see that every single one is completely different to the next. So we start with some of the moons inside the rings, these shepherd moons. These are Pan and Atlas, and they have very strange UFO type shapes. And initially we thought maybe they are shaped like that because when they were young, they were quite soft material and they spin really quickly, and then they get flattened at the north and south poles, but elongate around the equator. But actually what's happening is these moons are orbiting around Saturn within the rings and accreting or collecting ring material around their middle as they go round. And that's why they're these funny shapes. But they're really quite beautiful. And again, the pictures are quite incredible. Now, there are some very small moons. For example, Daphnis, only 8 kilometers wide, lives within the rings as well. But what you can see is that these moons are able to make features in the rings. And sometimes the moons are first spotted because of the features that they make in the rings rather than because of the moons themselves. So these kind of ripples or prominences in the rings that they create, because like I said, some of these moons are very small indeed. But again, the pictures are just impressive. I mean, this one looks like a surfer surfing on the ocean. And here you can see ripples and perturbations in the rings because of the moons that live within them. Then we have moons like Prometheus. It's a shepherd moon in the F ring. It's a really funny shape. It's heavily cratered, and it's got an ugly twin sister called Pandora, which is even more cratered because of living where they do within the rings. Then you have Epimetheus and Janus, which initially was thought to be just one moon, but it's actually two moons. And the reason that astronomers thought that it was just one moon is because these two moons actually share the same orbit. Now, this co-orbital motion is completely unique in the solar system. It's the only place in our solar system that we know that this exists. So the two moons share an orbit, and one will be in front, and over time, gravity will make the other one accelerate a little bit, and then that one will be in the front, and then the next one, and they take it in turns in their orbit. And because of the speeds and the way that they orbit around Saturn, if you lived on Saturn and you were looking at these two moons, they would be making horseshoe shapes in the sky, which is really, really strange. And like I said, this co-orbital motion is the only place in the solar system that we know this exists. Then we have Mimas. It's one of the larger moons. It's got a really big crater on it called the Herschel crater, which was named after William Herschel. And on the other side, there are cracks in the moon because of the impact of that crater, of that collision that caused that crater. Now, if we had an impact of that size on the Earth, it would take out the whole of Australia. And it's quite impressive that that moon actually survived a collision that big. And now, if you look at the moon in a heat map, you would expect the crater to be quite hot because of the collision, the energy from the collision, but it's not that hot. And instead, it's got this funny heat map on the left-hand side of the moon there. For those of you that play old-fashioned computer games, it looks a bit like Pac-Man. And we think that this area of this moon is heated because of the material that makes up that moon. Maybe some bits of it are more thermally conductive than others. Mimas is also quite well known in science fiction. So hopefully some of you at home are screaming, "It looks like the Death Star," because it does. So those of you that have watched Star Wars, it looks like the Death Star spaceship. And George Lucas actually invented the Death Star before the first close-up image of Mimas was taken by spacecraft. So that's quite impressive. There are lots of unusual moons around Saturn, very, very tiny ones, very smooth ones, egg-shaped ones, potato-shaped ones. This one is called Tethys. It looks a bit like our moon. It seems quite normal, but if you unwrap its surface, half of its surface is tinged a sort of orangey yellow, and the other half is tinged kind of blue. And that's because of how it goes around Saturn and how many particles there are in this kind of sea of particles around Saturn. And some particles impact Tethys face on, and some particles impact Tethys at the back, and that causes this discoloration. Then there's moons like Dione. Dione is one of the bigger moons. It's made from ice and rocks. What you see here, these surface features were thought to be kind of like river channels or dried up riverbeds or something like that, but actually they're the edges of cliffs. So Dione has got all sorts of interesting features. It's not, volcanic activity or anything like that, but it is covered in snow and ash, and probably has ice volcanoes on it. Dione also has an oxygen atmosphere, but it's quite thin, and it's not enough to support life like us. And the oxygen is not coming from photosynthesis, but it's coming from oxygen trapped in the ice on Dione that melts and is released into the atmosphere, and then causes this atmosphere to be created. Then we have Rhea as well, very similar to Dione, but maybe a little bit larger. And it's the only place in the solar system that has a ring system like its parent planet. So it's the only moon we know of that has a ring system. It's a very thin, very tiny, very tenuous ring system, quite hard to spot with the telescopes, and was actually spotted with the electron data that came from the instrument that I was using for my PhD. But still very interesting to know that that this moon takes after its parent planet. Then we have Hyperion, made of like a kind of coral-like substance, very porous, very light, very, very strange if you think this moon is still part of the Saturn family. And then there is Iapetus as well, and it's got this massive ridge around the centre because we think these two hemispheres smashed into each other, causing this ridge around the centre, a bit like how some of our mountains have been formed on the Earth. And Iapetus is quite interesting because it has a highly inclined orbit, which means it orbits around Saturn, but at an angle, and it travels out really, really far. So the blue rings on this picture are most of the other moons orbiting around Saturn in the centre, and the red ring is Iapetus's orbit around Saturn. And so you can see how far out it goes. So when it is at the edges of its orbit, it probably sees Saturn a bit like this. So imagine being able to see Saturn from a moon going around that planet. I think that would be really cool. Now, Iapetus is interesting because it's also discoloured. It's got a light side and a dark side. And again, it's quite prominent, it's quite obvious, unlike our dark side of our moon, which isn't a dark side, just a far side. But if you look at Iapetus, if you unravel a map of Iapetus and have a look at it, you can see the black side is very, very dark and the light side is very, very light. And it's quite specific, it's quite well defined as well. So sometimes people call it the Dalmatian moon because the material is kind of spotty in its darkness. And the reason that it's got this is because on its orbit around Saturn, at the edges of its orbit, it meets this moon here. This is Phoebe. Phoebe exists and orbits around Saturn at 12 million kilometers away from Saturn, and it also orbits around Saturn in a sort of tenuous, extended ring, which is that far away from Saturn. So Saturn's a tiny dot in the center, and there's this ring of material at Phoebe's orbit, millions of kilometers from Saturn. Now, as Iapetus goes through its orbit around Saturn, it meets this material at Phoebe and becomes discolored, black and white, depending on which face goes into the material. And so it's the same face every time. There's two more moons I'm going to tell you about. So there's there's Titan. I've already talked about Tethys. Titan is one of the biggest moons in our solar system. It's bigger than the planet Mercury, and it's very interesting to us because it has an atmosphere and it has lakes and rivers and a liquid on its surface, and that is all quite mind-blowing when you think of this as a moon of one of the planets in our solar system. Now, the liquid isn't water, it's liquid methane, which is a gas on the Earth, but it is a gas created by biological processes. And also in the atmosphere of Titan, there are what we call tholins, or these sort of carbon-based complex organics, which we sometimes think of as the building blocks for life. And so it's quite an interesting part of Saturn, and this is why the Huygens probe was due to land on the surface of Titan. It was not without its own issues though, because the probe was created and it was put on the side of the Cassini spacecraft, and during its time getting to Saturn, Beagle 2, a UK Martian rover, was lost at Mars. And so public opinion about things that were built, space objects that were built by the British space industry were, you know, the public opinions about them were not very high, and Huygens probe was a mostly British probe and a European probe. So when it got to time for releasing Huygens from Cassini to land on Titan, everyone really held their breath. And it did actually have a problem with how the data was going to be sent back. And if it had been ejected from Cassini at its original time, it wouldn't have correctly sent the data back, and all the information would have been lost. But the navigation team helped find a solution, change the trajectory of Cassini, and so the data did actually get sent back very well. And it's really lucky it did, because the information it taught us about Titan has been quite impressive. So Cassini ejected the Huygens probe, and it parachuted down onto the surface of Titan. And at the time, we didn't actually really know what the surface of Titan was going to be like. I'm just going to fast forward. This is real data. These are real photographs stuck together to make a video of the probe landing on Titan. So you can see mountains here. It looks just like a computer game image, but it is real data of this probe landing on the surface of a moon in our solar system. And actually the Huygens probe did also win some Guinness World Records at the time for being the furthest landing of a man-made object. And that was held by the Huygens team for quite a long time. And when it landed, oh, hang on, I'll fast forward a little bit more. When it landed, it ejected its parachute and took some photographs and took data on the surface of Titan, and was really quite revolutionary. So you are seeing now, and there you can see the shadow of the parachute, you're seeing now what the surface of a moon of Saturn exactly looks like. Really, really impressive stuff, built by human beings and sent to Titan. Now, just fast forward. So it was quite funny, because at the time there was a lot of press coverage, of course, but the press often get things wrong. And one of the articles said that the Cassini-Huygens project brought back rock samples from one of Saturn's moons, and unfortunately it did not bring back rock samples, it just landed. And another article said that the surface of Titan was a bit like creme brulee. So it had like a solid crust, and then as you cracked down into the crust, under the crust, it was kind of like a jelly or a mushy layer. But the Huygens probe was very, very impressive. It sent back, you know, it landed on Titan. It lasted. It took about half an hour of data from the surface. It took about 2.5 hours to float down. 30 minutes of data doesn't sound like much, but it was really quite impressive at the time, considering it was battery powered. It couldn't be solar powered. And when the idea was conceived, we didn't know what we were landing on, so it had to be built in such a way that if it landed on rock or creme brulee or liquid or solid, it would still last, and it did. So it was really quite impressive. And the surface of Titan has strange sand dunes, and it's got these rivers and these lakes, and so it reflects sunlight just like the lakes on the Earth. And the lakes and the rocks around the lakes can move and erode, and chunks can break off and swim away into these lakes. It's all just so incredible. At the equator, around the center of Titan, we think the lakes are part of a sort of tropical marshland where there's depths of pools up to sort of ankle or knee deep, and are probably caused from underground upwellings of liquid methane rather than the rainfall. But there is a cycle, just like the water cycle on the Earth, but a methane cycle that does exist on Titan. So it is a really interesting place to look at. And we think it's got all kinds of other things, like maybe underneath that liquid surface there's rock, and maybe a water ocean. There's interesting features on the surface of Titan, like this little storm or this swirling green gas which popped up as if from nowhere, and was probably again due to the seasonal changes during the Cassini mission. So Titan's really interesting to us because of the idea of astrobiology and the similarities and differences of Titan with a very young Earth. And if we could go back to Titan, there's lots of things to still look at and lots of areas still to map, although we have done quite well. Now, this was the last image of Titan that Cassini took before it went to its death in Saturn's atmosphere. But it was a really, really deep look and deep understanding of the moon while Cassini was there. And so if we could go back, we would like to send maybe a raft to swim about in the methane oceans, or a blimp, or little drones and things to fly around. And, you know, it would be amazing. And it's the sort of thing which is a next generation project. So some of you that are listening today could be involved in the next generation of projects to send to Titan. Now, the final moon I wanted to talk to you about was Enceladus, much smaller than Titan, only about the size of England, covered in an ice crust. And Cassini flew to about 25 kilometers from the surface of Enceladus during its mission. And Enceladus was really interesting because during the Cassini mission, it was noted by the magnetic field team, the magnetometer team, that Enceladus was actually bending the magnetic field of Saturn. So Saturn has a magnetic field just like the Earth, but Enceladus was actually causing that magnetic field to bend. And so the magnetometer team convinced everyone to change the trajectory of Cassini, to fly around Enceladus on multiple occasions to work out why it was bending the magnetic field. And what was happening was, at the South Pole, there are cracks in the ice, and from those cracks, there is material being ejected in plumes. These plumes of material are made from water ice, salty water ice, nitrogen, ammonia, carbon, sulfur, all kinds of impressive things. And so Cassini flew through the plumes of material a few times and analysed what these plumes were made from. And the plumes are really interesting for two main reasons. Number one, I showed you this image at the beginning, and this E-ring, and I said the E-ring was created by water ice and vapor and water ice and vapor, and we didn't know where it was coming from. But actually what's happening is that Enceladus is spewing out this material from its plumes at the same time as orbiting around Saturn, and it's actually creating the E-ring as it goes round, which is really quite impressive. And here is an image of that. So you can see the E-ring here of Saturn, and there's Enceladus with its little plume in it, and the images are just quite incredible again. So there you go, that's one of the images of Enceladus's plumes as taken from Cassini, and the surface of Enceladus as taken from Cassini. So quite impressive. And the plumes were analysed in detail, and the composition includes water vapour, methane, organic molecules, carbon monoxide, ammonia, sulfur, lots of interesting things. And we believe from models of the plume that underneath the ice crust there is a water ocean with all those different chemicals in it. And all the sort of requirements for life on Earth, particularly in the form of microbial life, extremophiles that live at the bottom of the ocean and feed off hydrothermal vents on Earth, that type of model, that type of system and environment could exist on Enceladus. So if anyone asks me, do I believe in aliens? Do I think there's life outside of the Earth? This is where I'd first point to, because we're not talking about intelligent life, but microbial life could live in the oceans of Enceladus. And because it's a closed system, it may have stayed like that for hundreds of years or even more. So it's really quite impressive for a small moon. Although it was postulated in the 1980s that Enceladus was active. And Enceladus is also interesting to me because it was discovered by William Herschel, the first president of the RAS, using this telescope on the right-hand side, which actually made up our logo until last year when we updated our logo. And the tube of that telescope is now at the Royal Observatory Greenwich. So we had a Cassini meeting at the Royal Observatory Greenwich in 2009. I'll change this before you try and spot me. Now, Enceladus, for a small moon, was very impactful, as I've shown, but the problem with changing Cassini's trajectory so many times to look at Enceladus so much meant that it ran out of fuel, and we had to end the mission. Although it was extended for many, many years, the mission did still have to come to an end. So there was lots of discussion as to how to end the mission. The spacecraft was running out of fuel. Do we send it off to the edge, to the further reaches of the solar system? Do we bring it back towards Jupiter? What do we do before it runs out of fuel? And it was agreed that instead of doing any of those things, we would fly Cassini through the gap between the planet and the rings and then let it burn up in the atmosphere of Saturn, rather than trying to crash it onto one of the places like Titan or Enceladus where there might be life, and we didn't want to contaminate anything within the Saturn system. So it had to go and burn up in the atmosphere of Saturn to abide by the Planetary Protection Act. So we did just this. And again, the views of the last few orbits and the last bits of the mission were quite impressive. Although we had, although you can look at Saturn and look at the rings and imagine that the bit between the moon, between the planet and the rings, there's nothing there, we'd never actually taken any data from there. So this was the first time that we actually flew through the gap in the rings. And this is a sound file, but it's not working, so have a look for it on YouTube. But what this shows, all the yellow and orange are particles, and the green is empty space, or almost no detectable particles. And here, where this arrow is, this is where Cassini flew in between the rings. And you can see that that area is actually pretty empty of particles. So for the first time ever, although we thought that was the case, we had evidence to prove that the bit in between the planet and the rings was empty. And so Cassini eventually flew on its final orbit, taking its final pictures of Saturn, and then eventually burning up into the atmosphere of Saturn, loss of signal of attitude, and then eventually it would be no more. And now this was quite sad because people had worked on the mission for 35 years, some of them. And so watching or understanding that a spacecraft that they had worked with for 30 odd years was going to break up in the Saturn atmosphere was quite emotional. And it only took a matter of minutes to break up in the atmosphere. But it did send data back all the way. It was orientated so that the antenna was pointing towards the Earth until the very last moments. And so it did send data back right until the end. And even though it was emotional, it was also quite bittersweet. So it, because of the time delay, it would have sent the data back, but it wouldn't have reached the Earth until 83 minutes later. So we knew about the death of Cassini 83 minutes after it actually happened. And during that time, there was a massive send-off party at NASA, where they invited a lot of the Cassini scientists to celebrate Cassini's life and share memories, and some, got quite emotional, and there were some tears as well, because Cassini wasn't just a spacecraft by then, it was all the people that had been on the team, and all the science and all the data and all the inspirational qualities of the Saturn system. So the Cassini mission was inspirational and emotional, and the team was a family by the end of the mission. And some of the team said, instead of thinking that Cassini broke up in the atmosphere, it was just giving Saturn a very, very big hug. Now, the interesting thing is there are still lots of questions to ask about Saturn. There are still lots of things we don't know. We don't exactly know everything about the rings, where they come from, where they're going. We don't exactly know the length of a day on Saturn. There's lots of information about radio waves and magnetic field that we don't exactly know. But there's so much data, even though Cassini, the mission ended in 2017, there's so much data that astronomers and scientists could analyze that data for another 50 years or so. And there are more and more academic and scientific papers coming out about Saturn and Cassini to date. So this is a picture of a picture of a science paper from June 2019, all about Saturn's rings and what the Cassini mission has found out. So there are new students now using Cassini data because there's so much data still to learn about. What's next? Well, there are future missions, not to the Cassini system, not to the Saturn system, but to Jupiter, and looking at Jupiter's icy moons and Europa, because Europa, which is one of Jupiter's moons, is believed to be very similar to Enceladus. So again, might have an ice crust with a water ocean underneath. And it makes us think about our solar system and planets and moons outside of our solar system, and what else could be achieved in terms of planetary science in the future. And I like this, this final quote from one of the Cassini scientists, who says, "Cassini has transformed our thinking in so many ways, but especially with regard to surprising places in the solar system where life could potentially gain a foothold." So I will stop sharing now. And if you do have any further questions about Saturn or Cassini, or anything space related really, please feel free to type them in the chat function. We've got a couple of minutes left for question and answers before we'll have to end this session. So if there are any other questions, please feel free. Please feel free to type them. Okay, so one of the questions that's come up, is it, okay, my grandfather contributed to Cassini but died before the launch. Wow, see, it really is a very, very impressive mission and very international as well. So is it true that the rings are going to disappear in the future? Well, they are, the ring particles are sort of drifting away and eroding, and some of the ring particles do come together to make moons, which then travel off into the solar system. But of course, Enceladus is still replenishing the E-ring. So it's kind of a cycle of ring material, where some material is lost and other material is created. So it will eventually lose its rings, but not for a few hundred years at least. But you know, it's being replenished at the same time. Are there any other questions? Like I said, we don't have to, they don't have to be about Saturn. Oh, there's a couple of shout outs which I didn't say before. Namishka from India, hello. And Birkenhead School Astronomy Club, hello to you as well. So, do methane ice worms really exist? So I think that's referring to me saying that there could be life on sort of Titan or Enceladus. We know a lot about extremophiles, so microbial life on Earth that can survive in extreme environments and can get energy from sources that are not the sun and eat unusual things like sulfur. And because we know about these extremophiles on Earth, we can postulate or estimate that maybe this kind of microbial life can exist in extreme environments on other places in the solar system as well. So that's why we talk about these, you know, the possibility of there being life on these moons of Saturn. Okay, what is the reason behind Enceladus bending the magnetic field of Saturn? Very good question. So the plume material that was coming from Enceladus was charged, and charged particles have magnetic fields interact with each other, and these charged particles were able to bend the magnetic field. Last question, what is a nebula? We tend to talk about nebulas in terms of clouds of dust and gas in the galaxy. So nebulas tend to be clouds of dust and gas. Oh, very last question. Is it possible for silicon-based life to exist? So that's the key thing, I suppose, when we talk about life in our solar system and in other places. We talk about life like us, and we talk about finding life like us. So we look for oxygen, carbon, water. And my biology is not very good, but I believe that silicon is almost as stable as carbon. So silicon life forms could exist elsewhere in the universe. But I believe that life, intelligent life that's out there, is more likely to be similar to us in terms of evolutionary processes, because of how we've evolved and how we've got here. I quite like the theory that if there is intelligent life out there in terms of aliens, that it could be kind of like octopus or something like that. But go and read more about that if you're interested. Okay, we are going to have to stop for today. But if you are interested in other space topics, or more in terms of Saturn and Cassini, feel free to email me via the Eventbrite links, or via my email address or social media, and I will always try and answer your questions. I hope you've enjoyed today's session. We will be running other sessions with the Royal Astronomical Society, so please keep an eye out for those as well. And stay safe and stay well. Take care. Bye-bye.